Okay, thank you very much. Very happy to give a talk in person again. So I'm very grateful to the organizers to have come through the struggles and organized it. Yeah, so I actually want to talk about a different project, which would be more related to integrability, but that is not in the stages yet to talk about. So I present something which is more in the a very geometric subject connected to dualities. But I hope I try to be very basic, and please interrupt me if there are any questions, because I know that there are many people from different fields here. And also, let me try to motivate it. And also one of the main motivations for me comes actually more from the side of integrable string sigma models. So the first point of motivation I want to make is, so what do I have these T-dualities, abelian, non-abelian, Poisson-Lie, or even more generalized T-dualities, integrability, and also, for example, non-geometric features of backgrounds like non-commutativity in common. It is that we need to understand the phase space, respectively the Hamiltonian formulation, well. So if we want to study dualities, we would like to understand them as like canonical transformations of some classical theory. If we look at integrability, we need to understand the Poisson structure to understand if the charges are commuting, and if we would like to understand if the backgrounds are non-commuting, then we would like to have some non-vanishing Poisson bracket between coordinates, for example. And so I want to have a very geometric point of view on this Hamiltonian formulation. And for strings, this has been done very long ago, of course. It's basically also the origin of what's called double field theory, or the general the origin of the connection to duality groups in generalized geometry. So how does it look there? So the Hamiltonian formulation takes a very convenient form in terms of geometry. Besides coordinates field X, which are just the embedding fields, the phase space is nicely parametrized, has nice coordinates, which can phrase in terms of so-called currents. And I mean, I will explain this later in a bit more detail. So, but these currents consist like of the canonical momenta and the spatial derivatives of the coordinate fields. And so this turns out that not the momentum alone, but this combination is a representation of this duality group. And also the other elements of the Hamiltonian formulation, Hamiltonian and Poisson bracket, take nice meaning in terms of generalized geometry. So we have generalized metric, and the Poisson brackets are characterized by an invariant metric of duality group. So this is known for 30 years, or probably more. And now the question is, we know a lot of things about these points above here for strings. So why not try to generalize that to other objects, for example, membranes and M theory, because we know we have similar things like double field theory or generalized geometry for M theory. Okay, so then the task is to find similar nice coordinates of the phase space, like this, to find a Hamiltonian and to find Poisson brackets for the membrane. So this would be like a chain of motivation if you're interested in one of these subjects. If you're interested in dualities, and let me give a different chain of motivation. So it's also to clarify the different kinds of groups that appear. So duality groups, if we have string or M theory compactified on a d-dimensional torus, we get the ODD group with integer values, which is T-duality, or kind of M theory, the EDD exceptional group with integer values, which is U-duality, which is an equivalence of different theories in different backgrounds, which give the same results, have the same content. If we now go to like the massless sector or consider supergravities compactified dimensional torus, we see that we can act with the with a still a global ODD or EDD transformation, but now we drop the Z, so it's like real number valued. So also this is like the origin of these groups, and it's very interesting. This is not the groups that will really appear in what will follow. What will appear is local ODD transformations, local EDD transformations, which can be thought of like it's a bigger group containing the gauge transformations of metric and the higher form gauge fields of the supergravity theories. So what one normally does, one has this motivation that these groups appear, and now we would like to have a geometric setup that respects these group symmetries. And there's two types of setups which I will use interchangeably, but other people differentiate strongly. So one is called generalized geometry. So instead of looking at only the tangent bundle of a manifold, we generalize this tangent bundle, and notions defined in the tangent bundle to a generalized tangent bundle, and these duality groups will act linearly on these extended tangent bundles. And a related setup is the one of double and exception field theory, which goes further and doesn't only extend the tangent bundle, but the whole space-time. So we extend the space-time in a way that we can act with the groups ODD or EDD, and then we phrase it in a way that we can make a constraint that is dually covariant and reduce back on the physical D coordinates. So another question is, why might we do that? So we see that these dualities are there, and yeah, as we would like to organize things in a way that we see the action of the dualities. Also, it turned out that it is just a very nice way to organize degrees of freedom and moduli of compactifications. And another reason might be that these dualities allow for slightly more general backgrounds than you would normally consider. Namely, you could, instead of just doing like diffeomorphisms and p-field gauge transformations, when you go from one patch to another, you could also do duality transformations. And these things are normally called non-geometric backgrounds, and they would also be included in one of the two setups. So this is the normal way how to approach generalized geometry. You start with these volume dualities and try to get a space-time geometry setup that is respects these groups in some way. So now I want to go the opposite way and start with some generalized geometry setup and want to see what kind of world volume theories are like the canonical ones. As we will be clear that the similar structures as in the string case appear, just with a different duality group, and like to investigate those. So this has been done for strings and had big success in describing generalized dualities, classical integrability, and now I would like to extend that to arbitrary world volume theories in supergravity theories like d-branes or membrane in M theory. Okay, so the program for the talk as follows. I will review some basics of generalized geometry, review the things a bit more explicitly that I have explained in words so far for the ODD string, and then generalize to the exceptional case. So let me start by reviewing what these extended tangent bundles, generalized tangent bundles are. So for the Riemannian geometry, which is associated to point particles, we consider the tangent bundle, and we have the group GLD acting on the tangent bundle. For the string, we take as the generalized tangent bundle tangent plus cotangent bundle. And turns out that this bundle has a canonical invariant. It's just a pairing of vector fields and one-forms. This we call eta, and we have like an associated structure which acts on that bundle. And yeah, similar things we can do for the exceptional theories as well. So for the in 4 dimensions, so we consider really a 4-dimensional manifold M, and then we have an extended tangent bundle, which is tangent bundle plus 2 forms. Or for higher dimensions, we also allow for 5 forms. And in this case, turns out that the invariant is not, cannot write down the invariant as easily, but we need a second bundle. So for the Riemann geometry, we only had the tangent bundle and then nothing else. Already for the string, we have a second bundle, which is just functions. So it's no index, but for the exceptional case, we actually have 2 kinds of bundles, 2 kinds of generalized tangent bundles, which are associated to 2 representations of what will be the duality group. So this is duality group E44, which is the is equivalent to SL5. This is E55, which is equivalent to the spin 55 group, and then there's E66. And it turns out that each of these groups has an invariant, and we can write the invariant always in the same way for all the 3 cases. Like that, it's an invariant that has 1 index in this kind of bundle and 2 indices in the R1 representation. And it also extends to the ODD case. Okay, so now you might ask, why do we do that? We do that because we can, on these kind of bundles, we can define the generalized Lie derivative in a nice way. So yeah, we have the, as in the Riemann case, we have the Lie bracket on the tangent bundle. Instead of that, we want to define a Lie bracket or something similar for generalized vectors, which would be an element of these bundles. So for example, they look like that, we have a vector plus a p form. And we define such a generalized Lie derivative. It's also called Dorfman bracket. This is why this index d is here. As the vector part is normal Lie derivative, then we have Lie derivative on the second form and this kind of combination. So in this form, it doesn't look very, as it has anything to do with the duality groups, but you can rewrite it in indices. So now we write these phi as these big kind of indices. So instead of from 1 to d, they go to 1 to 2d in ODD case, or 1 to 10 in this case. So they go over the vector indices and all the 2-form indices. And if you write that in components, see we have like a Lie derivative part, and then a part which is defined as so-called Y tensor. And the Y tensor is just defined in terms of these invariant structures of these duality groups. So we have some kind of bracket structure that respects the action of these duality groups. It's the first thing you want, and we have to note that this bracket is not skew-symmetric, so it's not a Lie bracket, but fulfills Leibniz set of Jacobi identity. Okay, and then the last column here, we want to have an additional structure which describes some kind of background geometry. So in Riemann geometry is symmetric, but it turns out for string and for M theory, we can package the background geometry in this way. So we can have a generalized metric, which in the ODD case, which encodes metric and B field, or in case of the M theory metric and the 3-form gauge field. M theory, the concrete form will not be very important. The following, just see that it has these big indices, so it is valued in the symmetric product of these bundles. So the duality groups act linearly of them, and if we have dualities acting, we just multiply these elements, the duality groups, by this metric. Okay, so now I have given the generalized geometry picture. I have extended the tangent bundle, Instead, I could also extend the manifold. So I extend the coordinates. Instead of the d coordinates x, I could include like dual d coordinate x tilde. So this would be the case for ODD. So I have two-dimensional coordinates on which the ODD could act. And similar for example, this kind of setup, I could have normal coordinates, then dual two-form coordinates, and dual five-form coordinates. So if we do that, we in the end would like to reduce again to d physical coordinates. So in this case, we have supersection condition or strong constraint. So if we have two functions f and g, we would like that this product of this form vanishes. So where this is the invariant tensor of the duality group. And then a small side comment to simplify the notation in this talk. I only work on one type of solution of the section condition, which is the M-theory section, and I only work if we imagine this as the internal manifold of our compactification. So I only work on that, and I'm not interested in like the effective theory that gets out for the other coordinates. So there's no spectator coordinates, or however you call them. So we're just interested really in a theory in d dimensions. I don't care about the rest. So this would be like the basic for what people normally do in generalized geometry. It turns out, if we look at world volume theories, which are defined in the end in these kind of geometries, it's practical to consider an additional object, which I call the omega symbol. So instead of this Y tensor before that defined the generalized Lie bracket, I define a P tensor, which is given similarly, just that we add this omega term here, and this omega term is defined in a way that we would write the canonical Lie bracket on the extended tangent bundle. So I mean, we can look at these kind of bundles also in a very canonical way, and we can look at the Lie derivative of a vector field on a P form and skew symmetrize that. So instead of doing that, this part would be a Lie derivative. So, and if we do that, we get such kind of an expression also using these kind of big indices. But of course, people normally don't do that because this omega bracket is not an invariant of these duality groups. So it's an additional object, and often it is skew-symmetric, but it's not skew-symmetric in general in the two R1 indices. Okay, and it's only more a side comment for people working in that field that this choice or the adding this omega to this setup, which breaks the duality invariance, seems weird, but in the end, it's really one can find that the choice of omega corresponds to the choice of section up to a trivial gauge transformation of the B or C field. So in the end, if we choose a solution to the section condition, so we choose D physical coordinates, it's the same as choosing one of the omegas. So on some level, we don't do anything new by considering this kind of objects. Okay, so, and before we continue with the rest, let me give some concrete forms. It will also not be important, but just for you to get an idea. So for the ODD form, this eta symbol is just the invariant ODD. So we have two identity matrices here, and the omega symbol looks nearly the same, just with a -1 here. And so the eta symbols for the EDD, they're of course more complicated objects, but in the end, they are also just delta symbols which contract objects. So they contract a vector with the two form, and then we get like a one form out. So it's not It's nothing very complicated. It's just very messy in the end. And the omega symbols are defined in the same way, just with different signs. So this is also just a side comment. Okay, are there any questions for that so far? Okay. So if not, let me continue and review like this, like the motivation why we would look at generalized geometry at all. And so the reason is we start with generic sigma model, string sigma model in d dimensions. So I don't assume any special properties on G and B. And I look at the Hamiltonian formulation of that. And turns out, as I said in motivation, that everything in the Hamiltonian formulation can be phrased in terms of object of that ODD generalized geometry that I've introduced so far. So first of all, it turns out that we look at this current. So this P is just the canonical momentum corresponding to this Lagrangian. The X are the embedding fields. And this current, if we combine the momentum and the spatial derivative, have this big M index, which is the R1 representation of ODD. And then it turns out, in terms of this current, we can rewrite the Hamiltonian just linear as the Hamiltonian or the generalized metric times these currents. So it's like quadratic, generalizing the free point particle, Hamiltonian of a point particle is the quadratic momenta. It's just the same way, just writing it with different kind of indices. And the spatial reserve constraint also just takes a form in terms of ODD geometry. It's quadratic, but with respect to this eta metric, the invariant metric.
Excuse me, where those special Virasoro constraints come from in general dimension?
I mean, this is D targets D.
So you do some functional derivative with respect to metric on the world volume or whatever?
Sorry, I didn't understand.
You do some functional derivatives with respect of a metric on a world volume?
Yeah, exactly.
Yeah.
Yeah, thank you for the question. And of course, you also get the time. So this part here, the part under the integrals, of course, the time-like resort constraint, it also vanishes. So the Hamiltonian, of course, also vanishes. I just separated here to see that you have different, like the different parts of the generalized geometry come into play here. So we have that can very select, but what's missing is, of course, the Poisson bracket. So if we just write the canonical Poisson brackets for P and X, and now we just rewrite it and use this big M index, what comes out is this following expression. So the Poisson bracket of the EM with the EN is given by the term by the eta invariant tensor times the derivatives of the delta function, which we also saw in the last talk a lot, and then the omega term with the sum of the derivatives. And yeah, in many settings, of course, these parts like this are zero. So if we do that and we neglect terms which are total derivatives under the spatial Wilczek integral, so we neglect terms which look like that, then we get something which I call the Dorfman-Poisson bracket, which looks much simpler and is also only defined in terms of the original generalized geometry. Yeah, and I think this was where this already generalized geometry was first discovered in these papers beginning of the 90s. Okay, so I mean, I will mostly use this bracket here, this watching out for these total derivative terms is not important in the classical theory much. It's just winding modes in the end, which come into play additionally. And yeah, there have been some papers on relating these to like if you do the quantum theory, but I will not do that. Okay, so we have now a Hamiltonian formulation which is just defined in terms of objects of only generalized geometry. And yeah, let me give some comments on that. So if we look at objects which are like just functions on the phase space, which are like contractions of functions phi m of x with these currents, if we look at the Poisson brackets of these sections, then we see that they just correspond to, if we use this bracket, we just reproduce the generalized Lie derivative on the phase space of the string. And if we use this kind of Poisson bracket without neglecting the total derivative terms, we get, of course, a Lie bracket, as we would expect. So we reduce the brackets introduced in the generalized geometry on the phase space if we just rewrite the Hamiltonian formulation like that. Okay, then we can also do like a interpretation in terms of extended field theory. And this turned out practical if we assume that the Hamiltonian doesn't depend on the coordinates, then we kind of just rotate freely around on the coordinates. And if we define the momentum to be the derivative of these dual coordinate fields, then it turns out we can write the current as like in its duality invariant form in terms of like a double coordinate. So the dual coordinate would have the meaning of being like a non-local contribution of the momentum, because we have to integrate it to get the momentum. So then something which was also done last week in the lecture, we can go to the generalized flux frame. So we can diagonalize the Hamiltonian. So we go to choose some generalized vielbein. So we redefine the currents with this EAM, generalized vielbein that makes this Hamiltonian of this form. And then it turns out that the whole information about the background is in this form. So we have that now this Dorfman Poisson bracket has this normal term which remains unchanged because this generalized vielbein leaves the metric invariant, but we get that the background information in these generalized fluxes introduced here. And so this has some nice consequences. So we can compute the equations of motion from that and see that in general, the equations of motion for an arbitrary background, you don't need to assume anything, look like that with these generalized fluxes. And yeah, so this kind of Hamiltonian formulation has been very useful to derive T-dualities as canonical transformations. So in the backgrounds which are used for T-dualities, these are special backgrounds, so these fluxes are constant, and then one can analyze canonical transformations on that background. So there's a lot of literature on that since the mid of the 90s. And this kind of formulation was also used to derive that certain backgrounds are like non-commutative in some sense. So we can go back from these currents to like define virtual new coordinates x, a, and then calculate what the like virtual Poisson brackets of coordinates are, and then we see that they must be non-commutative in some backgrounds. And then, just as a caveat, let me note that we can also derive this Poisson structure as a Dirac bracket from an extended canonical phase space. So we start with a phase space which is given by these big X and pi, which are commuting with itself, but have the canonical relations with each other. And then we do a constraint, which is that we identify this P, big P here with the current. And if we compute the Dirac brackets, we reproduce this Dorfman-Poisson bracket. So this was the review of the ODD case, highlighting that the generalized geometry is useful to formulate the Hamiltonian formulation of the string. Are there questions on that? Okay, so if not, then let me go a bit quicker. So now we want to generalize that to the exceptional case, and there are some challenges. So first of all, for the string, there's just one string in one kind of string in string theory. So we don't have different kind of word volume theories. In M theory, we have different kind of objects, and also in string theory or in like 10-dimensional supergravity, we have multiple possible word volume objects of which we like theories. So how do we differentiate between those? It's a question. Then we had in the exceptional geometry case, we had a generalized metric, so we could define the Hamiltonian in the same way. But then we had these eta symbols, which had an additional index in the exceptional case. So the question would be, how do we define the current algebra and the diffeomorphism constraints, which were defined before in terms of this invariant? So the closest thing would be that, but it has this extra R2 index. So the solution would be that we need an extra object in R2. So the other question is the extended target space interpretation is very natural in the string case because the dimension of the R1 representation is just 2D, and it's also the number of coordinates fields plus number of momenta. But this is not the case anymore for the exceptional field theories. So the role of the extended coordinates is not entirely clear. And let me mention that there's also a bunch of people who worked on that before, and yeah, I will like combine the results into a single expression. And maybe in view of time, I jump the membrane and will discuss the generalized setting directly. So what I want to define now is a p-brane world volume theory with EDD symmetry in the same way the string Hamiltonian formalism was defined. And the first thing was explaining is that we need some kind of object which is in the R2 representation. This will be a p-1 form on the world volume. So we work on a p-dimensional world volume now, and this is supposed to be closed. And then this is similar to the fact that we could define the current E before in terms of the derivative of the we define now a p-form current on the world volume like that, like the construction of this charge with the extended coordinates. And we contract them by this invariant tensor. So we have, again, currents which take elements in the R1 representation. And then this general setting, I postulate that the current algebra is given by this. So for the string, we had that the Q was just 1. So they would produce that, and we had no curly K. So for the setting, it looks like that. We have the Hamiltonian and the spatial diffeomorphism constraints, which are defined in the same way. And the spatial diffeomorphism constraints, we have multiple of them. So this is this free index K. And normally this expression is like overcounting them. And the set is reducible. So now we want to specify what this charge Q is, because this was so far just an arbitrary p-1 charge on the target space, or put back to the world volume. So what I now require is that we look again at these sections of these currents on the phase space, and we require that the Poisson bracket of those correspond to the generalized Lie derivative. And what comes out is that we get an equation for the charge. So if we want to require that the Poisson bracket of these sections becomes the Dorfman bracket, the generalized Lie bracket, we need to require that the charge and the positions are combined together with the currents like that. And then we reinsert the definition of the currents from here into here. And then we have now a condition where we have both sides the charge is, and we can solve for the charges. So the role of the charge will be twofold.
Well, let me ask a question. It looks natural that Q should define in some sense a symplectic form of Poisson bracket, and which is more or less the same thing as your Dorfman bracket. But as I look at your condition, this Q will depend on Z, maybe linearly, or in which way? So in string case, it doesn't depend on Z, this Q. And so what kind of dependence it is? It can be absorbed maybe in the structure constant of F, you know what I mean?
So you can define some kind of, I mean, we'll discuss how this Q looks. It will be like for the membrane case, which I skipped, it is just the differential X. It's just a bond form. It's linear, yeah. It's just a bond form, and so it's just dx mu in the case of the membrane. But you will see the solutions and the role takes. So so the role of the charge, I will discuss the solution on the next slide, is twofold. So we don't have only one solution; we have multiple solutions in general, or none, depends on both P, the world volume dimension, and D, the target space dimension. So the role of the charge specifies the object. So it could be multiple objects which are allowed in the theories, and also projects out certain parts of the description. So in this currents, yeah, if we have a certain solution, we will not have a full, so this charge, once charge solution breaks this EDD symmetry, and we will see not the whole background. It's like we could define a membrane in M theory, but it will not couple directly to the like the dual field, which correspond to the M5 brane. And yeah, let me also mention that this charge condition reproduces different approach by Avanitakis and Blair, where they derive different actions. So the general strategy is we specify the section. So if we go to M theory or to type 2B supergravity, we find charge solutions and get the Hamiltonian formulation. So for ODD, the charge is just a number. The charge condition is automatic. You would say if Q is not 0, it would be a string. If Q is equals to 0, there would be no currents. So this expression becomes that in the string case. For the M theory sections, for P small equals to 0, we have two solutions. We have the M brane. There, this Q is just the form dx mu. For the M brane, I will discuss it soon. And for the type 2b section, we have different kinds of solutions. So we have for p equals 1, for example, we have two kinds of solutions, which is the string or the D1 brane. For p equals 2, there's no solution. For p, D brane, and so on. So, and if we look at the Hamiltonian formulation of those, we would just get the Hamiltonian formulation of the typical D brane actions or the normal string sigma model. So the rather interesting thing is that this charge condition, it was just derived in terms of generalized geometry. The solutions of this corresponds to the half BPS objects of the supergravity solutions. Okay, and yeah, in view of time, I will go to the conclusion. And yeah, so maybe just mention that, for example, for the p equals 5, we need to go to d equals 5 or 6 to get the solution, and there this Q will be a 4 form, and will have such a form. It will not tell you much now without spending too much time on it. So let me just go to the outlook. So what we have seen is that we just defined the setup of a Hamiltonian formulation of arbitrary p-brane objects and defined it in a way that it uses objects of generalized geometry, and then want that on the phase space somehow there's this generalized Lie derivative realized, and then we got only that certain objects are allowed. And these were the half BPS objects, and so and then if we go through this setup and try to understand what these currents then mean, it was possible to always reproduce known actions. So for the membrane, we got the bosonic membrane action for the M5 brane. I didn't show that now, but you also reproduce known 5 actions. So the first question would be, there's also NS5 brane solutions to this charge condition, KK monopole solution to this charge condition. Does it also reproduce the known solutions of actions, like Hamiltonian formulations of actions, which were discovered in the 90s? And then it would be also interesting, there's these exotic objects in M theory and exceptional field theory to get any idea of dynamics, which it's not there in literature yet. Then one motivation of this program was to understand these non-perturbative dualities of M theory better, because in string theory you can make the Hamiltonian formulation totally ODD invariant. In the exceptional case, apparently not. And so now it looks very covariant, this formalism, but of course, still the M2 Hamiltonian formulation and the M5 Hamiltonian formulation have a different dimensionality, so you can't just map it. Then, so far, I haven't assumed any properties of the background fields. So the whole thing was just like kinematic. So there's no relation to supergravity, exceptional field theory equations at the moment. And yeah, it would be interesting to see if it's easier to derive something from this Hamiltonian formulation than from, for example, from the membrane action, from which it's not clear how to derive supergravity equations. Then it was interesting to get the non-geometric interpretations of these backgrounds. Then something which was also paper this year, how to derive this setup from some kind of AKSZ construction to extend it to the higher exception field theories where additional objects are expected. And yeah, then maybe the most interesting part for the audience here would be to study classical dynamics of these p-brane objects. So one thing which is also a paper from earlier this year was that Charles Strickland Constable showed that the membrane in SL5 follows something called generalized geodesic, following an arbitrary background with metric and the 3-form gauge field. And maybe this, with this Hamiltonian formulation, one can generalize this to similar descriptions. And then, of course, one of the original motivations was to derive non-abelian U-duality as a canonical transformation of some world volumes theories. And this, yeah, has done in certain cases by some authors, but maybe this could also help to investigate that. So this brings me to the end, and thank you.
Well, at the very beginning, you spoke about classical integrability. Mm-hmm. And at the end, you didn't make a remark of these subjects in this generalized setup. You know what it could be, Black's operator, if you have just several derivative respect to several loop variables. So what it could be, the LUX operator.
Yeah. So this is, yeah, I mean, this was one of my original motivations to understand what kind of, yeah, structures there might be. So one thing I wanted to do was to just like embed some integrable type 2A string into the membrane backwards, and to see maybe how, if at least like some sectors of membranes might be integrable, but I haven't found any literature on like the things where they look at membranes which are integrable or some LUX operators. So I would not know where to start, so I didn't.
So maybe that was in your examples that you didn't have time
Yeah.
to ask. But so how do you need to have very exotic examples to have a non-geometric setup, or can you have, or do you have simple examples where you need to have some non-geometric interpretation?
I mean, at this point, I mean, there's the standard examples for backgrounds which are non-geometric, and which would be like the Q-flux background in the M-theory setup. So let me. So, I mean, for the membrane, you could have, what let me spec. So for the membrane, the current on phase space looks like that. So we have the momentum and then the two form, which is dx mu dx mu. And if we want to go to the non-geometric interpretation, we go like to a generalized flux frame, and then we get an expression for these currents which looks like that. And then we could have, there are this also in the M theory, there's like a duality chain, and you get some backgrounds where you need to do U dualities along, if you go around a cycle, and there's corresponding fluxes to that. But then the challenge would be that in the string case, if we want to derive like what the Poisson bracket of the coordinates field would be, you just have to integrate, because there's just dx and dx sigma here, but here we have like a two form in these currents, and no one really knows how to handle going from this expression here, where also there should be a z here and not an e, back to the coordinates. So we would like include this expression here for the currents in here, and then would try to look for the Poisson brackets of the z with each other. And yeah, it's a weird expression, and I don't know how to, yeah. So this is why it was on the outlook and not the result.
So David, one precision. There is a construction which is called magnetic bags. This is sort of regions where people find a collection of magnetic monopoles.
Mm-hmm.
It looks like a description, a conjecture description is claimed to be TBI type. Mm-hmm. But I'm just wondering if you have heard of this, and does it fit into your formulations? Because it really looks like these generalized fluxes that you define here mm-hmm. would be actually an appropriate type of.
Okay. No, it's interesting. I haven't heard of that, but yeah, maybe we can talk afterwards about this. Yeah.